This is the fourth example on the conditional distribution. In this problem, the joint density function of capital X and Y is given by f of x comma y equals x times e to the negative x times y plus 1 when both x and y are positive. Part A. Find the conditional density of capital X given capital Y equals y, and that of y given capital X equals x. Part B. Find the density function of z equals x times y. Part A of this problem is straightforward. We just need to utilize the definitions and carry out a few computations. On the other hand, Part B of this problem incorporates a few different aspects of our study. By working on it, we could have a better understanding of the whole topic. So let's get started. In Part A of this problem, we would like to find the marginal densities for both capital X and capital Y first. As usual, to find the marginal density for capital X, we need to integrate the joint density function against y from negative infinity to positive infinity. Since our joint density function is only non-zero, from 0 to infinity, we can rewrite the expression in such a format with respect to y. The antiderivative is just given by x times e to negative x times negative 1 over x times e to the negative x times y. The final outcome is just e to the negative x. Similarly, the marginal density function with respect to y is going to be the integration of the joint density function with respect to x this time. A practice of integration by parts shows that the integral is going to be equals to negative x over y plus 1 times e to the negative x times y plus 1 evaluated as 0 infinity plus the integral from 0 to infinity of 1 over 1 plus y times e to the negative x times y plus 1 with respect to x. By finding the antiderivative of the integral, we end up with negative 1 over 1 plus y squared times e to the negative x times y plus 1 evaluated at 0 infinity. Hence, the final outcome is just 1 over 1 plus y squared. The second step is to form the conditional density. Based upon our computation, the conditional density of x given y is just obtained by taking the quotient between the joint density function, which is x times e to the negative x times y plus 1, and the marginal density of y, which is 1 over 1 plus y squared. Thus, the outcome is x times e to the negative x times y plus 1 times the square root of 1 plus y. Similarly, the conditional density of y given x is just the quotient between the joint density function and the marginal density of x. With simplification, we end up with x times e to the negative xy as the outcome. Let's explain the idea to solve part B before we implement the computation. The first observation is that the joint density function of z and x is given by the product between the conditional density of z given x and the marginal density of x. Therefore, the density function of z could be obtained by integrating the joint density function with respect to x. And this will be the roots that we're going to be taking in solving part B. So let's think about what is the conditional density of z given x. Z is defined as capital X times y. Hence, if x is fixed, the value of z given x is just equal to the value of y given x times the little x. We have computed the density function for y given x to be x times e to the negative xy. In other words, the variable of y given x is in fact an exponential random variable with parameter x. Consequently, the random variable z given x is a multiple of an exponential random variable is just another exponential random variable whose parameter is given by the original parameter x divided by the multiple, which happens to be x as well. And in other words, this random variable is an exponential random variable of parameter 1. Hence, we conclude that the conditional density of z given x is simply the density for the exponential random variable of parameter 1, which was known to be e to the negative z when z is greater than 0. Now, to find the joint density of x and z, we only need to multiply these two functions together, which is e to the negative z and e to the negative x respectively. Finally, to obtain the density for just z itself, we could integrate the joint density function from negative infinity to positive infinity with respect to x. Since this function is only non-zero when x is a positive number, we just need to integrate this function from 0 to infinity. And through computation, the final outcome is just e to the negative z. And this is our answer for part B.